Alright, in this video we want to start with the first of the three soft body constraints, and that is pressure. It's not the fastest or the simplest or anything, it's just the most unique one in my opinion, and that's why we start with it. It is actually slower than the struts constraint, and you will see it's actually not a good choice if you want something simple. Because what it does is it basically pumps an object with something like air or something, some gas. So it tries to keep its volume. It's a bit like a balloon. If you press on one side, then the volume will push to the other side. And this is what the pressure constraint is the only one able to do. So let's play around with this. And we start, of course, with a toy as usual. And if we look for the pressure node or something, we won't find anything. I'm not sure why that is, but you will find it when you look for vellum configure balloon. And here you see something special. We will see the same in the next two, and that is that the pressure constraint is built of two elements. The first one is actually a normal cloth constraint, and the second one only is the pressure. You can actually kind of understand the logic behind that if you look at the constraints themselves. So the cloth constraint is what we already know, the outer shell. And the second constraint, and let's disconnect the constraints, is basically, okay, it doesn't look like it to be fair, but this is basically what's inside. So this is important to understand. It's a combination of two constraints, the outer shell and the behavior that we already learned about it in terms of stretching and bending, and then the inner pressure that tries to keep the volume intact. Now let's stop with the talking and let's do something by just playing around with this. And if I activate the ground plane and let it fall down, you can see what's happening already. And you can see at first it looks like a normal cloth constraint, but here you can then see that the head falls down and basically the volume it created pushes his bottom up. So this is the idea behind pressure. It's actually, filled with something. Now be careful. If you look into the pressure constraint, your first instinct might be that you control this with a stiffness under stretch. Once again, stretch is a weird wording here, but they reuse the interface. So out of a habit, you would probably try to increase the stiffness, and let's do this quite a lot and see what happens. And what you would expect is that there's more volume, at least I would expect that. And not really. I mean, it seems a little bit like it, a slight bit more than before, but not really. And it's also not a matter of substeps, by the way. So if we increase the substeps, maybe that's the problem here, it will still not fundamentally change the behavior. And that's important to understand. The stiffness, the stretch stiffness does not control the amount of volume. It controls how strongly the constraint tries to keep its volume. It's not about how much volume it has. This is where the rest length comes in. And the rest length is something I think we talked about. It basically is the distance of the size of the constraints relative to the starting point. So if you increase that to, let's say, 3, what you basically say is the volume will be 3 times higher than it was when you created that thing. And what will happen is this. It will push it apart quite a lot, actually, which is a bit aggressive. Let's quickly lower the substeps to speed it up a little bit. And I think what we have to do here, so that it's not too crazy, is lowering the stiffness again. Because basically it just tried too aggressively to keep the volume. So here you see what's happening. It's kind of funny. It starts with that volume, and then as soon as we start calculating, it increases the volume 3 times. Now, this is still not really what we wanted, probably, because we don't necessarily want it to actually inflate, and this is actually something we will look at in another video, but we want it to keep its volume and not fall apart. And this is the third thing you have to understand. Let's go back to more or less the defaults. To keep its shape, you have to take the outer surface into account. So this is what you actually change in the cloth constraint. So let's increase the stiffness here, because actually by default it's pretty low. So it behaves currently a little bit like a literally balloon. So it's really stretchy. So it will implode very easily, or stretch very easily. So let's increase both numbers, the bend stiffness and the stretch stiffness of the cloth constraint that defines the surface. And now we will see it's much better. It should be, at least a little bit. Well, let's increase it further then. Try that again. And now maybe let's increase the stretch stiffness of the vellum pressure so that we keep our pressure intact. Yeah, now it's getting better. And now actually, I think what's still missing, even though it got better, as you can see, it's more stable, it's more, has more volume. Let's increase the sub-steps on top. Then we should get what we want. Yes, that's what I wanted. So now you really feel like it's more like a, yeah, like a swimming pool toy or something. And this is important. It's not just the stretch stiffness of the pressure constraint. You have to also control the cloth to define how strong the outer surface is. And by default, it's pretty low. And also you use the stretch stiffness to define how strongly the system tries to keep the volume. It does not control how much volume you have. For this, you need the rest length scale. So let's increase that to give it more pressure inside. And then, okay, it's still a bit too stretchy, the cloth outside. But you can see this is much closer to what we originally wanted, probably. So there's a lot of energy in there, so it wobbles around a little bit. But you can see now it basically behaves like we wanted. And just the stretch stiffness is not enough for that. All right, you can see this is not really usable for stuff like Jello or something like that, or maybe rubber. This is really only if you want to create something that is really filled with a volume. And one more thing you can do with that, like I said in the beginning, and maybe let's lower a couple of things again to show this. One nice thing you can do with this that you can't do with any other volume constraint is you can push the volume in one of the areas, so you can push it around. And for this, I created a little funny setup here to be mean to our toy. And this is animated, and we use that as the collision object. And you might already guess where this is going, and it's exactly going there. When you push a pressure constrained object together, then you will push the volume. You can push the volume out of one area into the other. It tries to keep the volume intact, and we will see this here in form of an inflated head. And actually, we can, to make this stronger, lower the stretch stiffness of our cloth outside of our surface material. And then we should see this even more, because then, you know, the material of the surface is more stretchy, obviously. And now you can see the idea even better, because again, it's more stretchy outside the head. And now you can see we can actually push the virtual gas, let's call it, out of the body into the head, which is kind of funny that this is possible. Now it wobbles around a lot here. This has to do again with the sub-steps. So let's maybe increase them and make the pressure a bit stronger, and maybe also the stretch stiffness lowering a little bit. And let's see how this looks like. Or just to get a feel for it. And I think now you can see it looks even better and shows pretty well the idea behind the pressure constraint. So just to finish this, let me quickly try that without the pressure constraint. And obviously, you know how this would look like. Let's lower the sub-steps for this, so to speed this up. And of course, you know, there's no pressure. Obviously, it's really just the surface that is pushed together and nothing is pushed around. All right, so the pressure constraint, as you can see, the special thing about it is that it actually calculates a volume inside that you can push around. And what's important here is that you basically have 4 different things, main parameters to change. The stretch stiffness in the pressure constraint is not what you would think. It's not the amount of gas inside, it's how strongly it tries to keep it. What's the amount of volume you have inside is controlled by the rest length scale. So increasing that will give you a higher actual pressure inside. Now, this is not the only one you can control though. The whole constraint comes in 2 parts. And one is the cloth constraint that defines the outer surface of your object. And this is very important to control the behavior, because here you can control, you know, how elastic or easily to bend it is. So a very important part of the whole setup. And the whole thing is not really made to do, you know, soft stuff that is not filled with volume. So rubber or jello or something is not good for that. This is really made for something that actually needs a volume preservation, like a balloon or maybe a pool toy or something like that. So keep that in mind. So yeah, that's a pressure constraint. I hope this is helpful. Thanks very much and see you later. Cheers.